welcome to this video on Ansys Fluent for mixing processes with a continuously stirred reactor. I'm showing a reactor here. It has 2 impellers, it has 4 baffles, and the objective here is to mix a small amount of one ingredient within a larger quantity of another ingredient. And both ingredients are liquids, and so we're going to use a species transport simulation for this modeling effort. I've placed a sphere here near the top, and this will be where our tracer will be released from. So I could also do this with a cell register in Fluent, but I decided to use, in this case, put a geometry body in the space claim model here to represent the release location. And I did that using the sphere option within the design display. And what we're going to do is we're going to have the top surface that will be a free slip surface, and the impellers, the inside regions, these will be modeled with frame motion to model the rotation of the impellers, and then there'll be a rotational velocity placed on the shaft. So to help that, I also place some name selections or groups to indicate different items, like the wall tank, that's going to be a stationary wall. The top I label as a boundary BC slip wall, and then my baffles, name them. And there's an outlet down at the bottom here. We'll assume that everything is closed for now, so that'll be a wall as well. I place groups or name selections for the impellers, and then for the wall shaft, I place the name selection for those as well. And that'll be used for the velocity specification. The only thing left here is to do the sharing topology. I already did that, and you can see once I turn on the display, then we can see the dark blue lines and the pink purple lines indicate that the geometry has been shared. So everything is ready to go to the mesh model. When it comes to meshing the model, I'm using Fluent Meshing, also known as Fluent Meshing mode. I'll be using the Watertight geometry workflow. So the first step would be to import the geometry. Once the geometry imported, we can start working on surface mesh. First option would be adding local sizing. In this case, I'll just leave that off. So update that, and then go to generate surface mesh. And with generate surface mesh, I'll use these sizes here, minimum size of 6, maximum of 24, and put the cells per gap at 2, generate the surface mesh. I can see here my maximum skewness is 0.52, which is very good, so I'll move on. In this case, I have geometry. In my case, everything is fluid zones, but just in case, I'll put that as the geometry consists of fluid and solids as cell zones or voids. I don't need a cap. Yes, I do want to change all fluid boundary types from wall to interior. This is important for where there's interfaces between the frame motion zones of the impellers and the tank body, as well as the tracer. I'll leave shared topology and multi-zone mixing off. Looking at updating boundaries. All of my boundaries are shown here are walls, so I'll keep that. Do an update. I do have 4 fluid regions, so I'll keep that as 4. And then in the update regions, we can confirm that the bodies, the regions are all indeed fluid. There's no additional voids or dead zones or solids, so I'll do an update here. In terms of adding boundary layers, I'll select yes. I'll add them in the fluid regions, and only on the walls. I'll use a smooth transition with 3 layers. And then when it comes to generating the volume mesh, I'll use the polyhex core, and I'll use the same min and max cell lengths that I did for the generate surface mesh. And we can see how the mesh looks. See, we have boundary layers on the walls of the tank, walls of the impeller, and we do have walls also on the top, but that will be a free slip boundary condition. The minimum orthogonal quality 0.2, so that's very good as well. So this is ready to go for these using the flow solver. In the flow solver for the steady state calculations, we'll walk down the outline view to see the setup. So starting with the general, which is already shown, you see that it's a pressure-based solver along with the steady in time, leaving gravity off. Going into models, multiphase and energy are both off, using the SST K omega turbulence model, and we've activated the species transport, so that model is on. Reactions are turned off. So now we have a mixture material that specifies the mixture template. So go into that. In terms of mixture species, I've already populated. So there's a CP and a TS. The TS I'm using to represent tomato sauce, and the CP represents carrot puree. So since the tomato sauce is the majority of the fluid liquid, I leave that as the bottom of the list, and this, CP, the carrot puree, is at the top. So okay out of that. And I'll go out of here. No discrete phase in terms of model, so I'll get into the detail of the materials. We have already seen mixture template. So the density, we're going to use volume weighted mixing law. Same thing with the viscosity in terms of mass weighted. And I'm assuming a mass diffusivity of 1e to minus 9 for the mixture. Getting into the details of each species, I'm assuming the material properties are the same for both the carrot puree and the tomato sauce for save a little time. So density specified 1025. Now viscosity, I'm assuming that both liquids are non-Newtonian in behavior. And to get this non-Newtonian power law pick to be available, one needs to activate using the TUI command. So to do that, I'll just go up to the quick search and type Newton. And that should bring up this suggestion. I'll double click on that. That copies it to the console. I'll hit enter, and that prompted for a yes. And so I'll type yes. And so that is what enables the pick for the non-Newtonian power law. And do an edit on that. And for both of these liquids, using a consistency index of 30 and a power law index of this 0.275, I'm limiting my viscosity to be within the range of 5 to 500. One could modify the scale here to see what that looks like. And maybe I'll tighten up the range so we can see how the behavior is, the viscosity as a function of strain rate. So again, I did both the same for both liquids. Getting into the cell zones, so the four fluid zones. 2 rotating zones are specified with frame motion. They're rotating in the negative z direction and using an expression to dictate the RPM, the agitation speed. So that is done for both of the impellers. So there should be the same settings for each one. And then the tank and the tracer are both stationary zones, and all four of them have the same mixture template for the material name. So no difference in the tracer. Getting into boundary conditions, we have 3 internal boundaries for the interfaces between the 4 fluid zones. And then the wall boundary conditions, so this top wall here is modeled as a free slip boundary, so I'm saying a specified shear of 0. And my baffles, my impellers, the outlet down at the bottom, the wall tank, these are all stationary walls, stationary no-slip walls. Then the shaft that is adjacent to stationary zones, I want to put a velocity on those. So I use a moving wall, the same rotation direction, -1, and the same expression for the RPM. And that RPM value is down here, expression. So I'm setting that to 200 revolutions per minute. Getting into solution methods, pretty much the defaults. Same thing with the controls. Getting into report definitions. One thing that might be helpful to know is what's the torque, so the power that is being used or subjected to the impeller. And so all of the rotating walls are used for the moment calculation. And my axis is centered on the z-axis, and then I want to specify that axis direction here is either plus or -1. And so getting into solution, so here we just want to solve only the flow and turbulence. We'll leave the species calculation turned off. Go into run calculation. This time scale factor, default value of 1, it might help with the solution early on. If there's convergence issues, bring it down, say to 0.1. That appears to be what I used here. I think that's it for the steady state setup. So we just run this steady state calculation out to get nice flat lines for the torque and moment, and you can see good residuals. And then we'll switch that over to the transient simulation next. So once the steady state calculations are complete, we switch over to the transient mode, and we'll also turn the flow and turbulence off and turn on the species equation, which in our case is CP. There's nothing to change in materials or cell zone conditions or boundary conditions. All the work that needs to be done is in adding the named expressions. So the order that I created actually would be looking from the bottom up here. So the first expression would be to calculate the volume average mass fraction of the carrot puree species, and that's done over all 4 cell zones. And then we'll start coming up with that tolerance range. So there'll be an upper limit for the 99% mixing. And so now I'm using half of 1%, so 1.005 times the volume average mass fraction of the CP species. And then for the upper limit for the 95% mixing, now it'd be half of that 5%, so 1.025 times the volume average. Similar is done for the lower limit. So the lower limit 99 and the lower limit for the 95. And then what we need to do is now create some logical expressions. But to do that, there'd be some expressions here. So I use a flag name. So it's in terms of if the species fraction of CP is now below this lower limit of 99.99, then the flag is set to 1. If it's above, then it's set to 0. And it's similar is done for the 95. So you can see it's a 95 here is new. And then also the 99 now looking above. So if the mass fraction is above the upper limit, which is out of bounds, so then it'd be flagged as a 1. And then if it's within the limit, it's a 0. So what we're looking for is if it's something is outside of the tolerance range, then it gets a flag of a 1 value. This is for the 95. And then to come up with the extremes left and right, above and below, I'll use a sum of those two flags. So above 95 and then below 95. So I'll add those two together. Same thing is done for the 99. And now I have a expression that's going to calculate the sum of those things. So I'll do 1 minus this expression. So it's summing up all of those cells that have a flag value greater than 0. So anything it's going to be like 1 or 0, 1 or 2. And so if it's greater than 1, then it gets summed up. And then in the denominator, there's a sum for the total volume. That same thing is done for the 99% mixing. The uniformity, there's just one expression. And that's doing a sum integral of the mass fractions throughout the domain. The next is to generate a cell register. And so I've generated these two cell registers here. One for 95, looking at cells more than an expression value of 0.5 for the flags 95 expression. The same thing can be done for the field value of 99. So using the flags 99 and then had cells have a value greater than 0.5. Yeah, you save for each one. And then we like to go to the surface create with expression volume. And that's what's used to calculate a surface for each of those field value cell registers. One for 95, one for 99. Just pick on one of those and then click on create. We actually have two of them already. So there's one here, and then those can be used in graphics to generate these mesh objects. So looking at this one, so I have the mesh of the expression volume for the 99% mixing. I like to use a uniform coloring, say red, make it stand out. And then the same thing for the expression volume of 95. Again, the red color. And we can make a mesh object for, say, the stirring surfaces, and then another one just for the overall stationary, say like the tank and the baffles. And these can get fed into scenes. So like this scene for the 99% mixing. It includes the expression volume for 99, the stir, and the tank. I like to put the tank just transparency something closer to 50. Same thing can be done for the T95. And then these scenes, these can be put into calculation activities. So to generate animations from them, an example here of the T99, I'm recording every 100 time steps, making a PNG image. I create a folder to organize them. And then down here in the animation object, I pick on the T99. You can preview it. Okay, to save. And back to up here for report definitions. We made these expressions. You can generate reports from them. So say like for the 99, the expression, I pick on my fractional volume. So the fractional volume 99, pick that, have it create both a file and a report. Same thing we done for the fractional volume 95. So the expressions now has the 95, report file and report plot. And finally, the uniformity index, generate a report with the expressions, picking on the expression of uniform. And once we have the report definitions, then we can generate the report files as well as the report plots. So that's the majority of the setup. What's left then is to check on things with the solution. In terms of methods, probably best to put this to a back-bounded second order implicit. And I think the default controls work fine. And double click again to check, make sure that only the species equation is active. And now we're using the current flow and turbulence, but now we need to patch the mass fraction of CP in the tracer to a value of 1. So we'll pick on the variable CP, value of 1, and then pick on just on the tracer and do a patch. And that completes the setup for transient simulation. I used a time step size of 1e minus 3. That gave me a convective Courant number roughly about 1. And so then you just run this out to the number of time steps that be needed to generate the complete mixing, at least mixing that gives you a fractional volume of 99%. That gets it out that far. In terms of results, the monitor files can be used to generate plots of the uniformity index and the fractional volume mixed over time. And so we can see here that the uniformity index value rises really rapidly early on, where the 95% mixing starts a bit later, and then the T99, the 99%, rises much later because it's a much tighter, more stringent requirement. And then the animations, the images that were used from the cell registers that were displayed. This gives a picture of what is unmixed. So the red represents what is unmixed in the reactor vessel after, say, about 300 seconds. Thank you for watching. Bye-bye.